students in Nat Warner's lab here at Penn State, and this is our milliQ system in our lab. The milliQ system provides extra filtered distilled water, which we need in lots of experiments in our lab, and it's currently not working. The milliQ system at the source requires 1 bar of gauge pressure to enter into the system to provide us water coming out. 1 bar is equal to 100,000 newtons per meter squared. And as you can see on this board, we have our Bernoulli's equation, which we can use to solve for the elevation head required to provide us with 1 bar of pressure at the milliQ system, which we can call our elevation 0. So Bernoulli's equation, P1 over the specific weight plus V1 squared over 2G plus Z1 is equal to P2 over specific weight plus V2 squared over 2G plus Z2. Calling the milliQ system our point 1, we can cross out our Z1 because we are assuming that this is an elevation of 0, and we can cross out both our V1 squared and our V2 squared terms because we can assume that there is relatively no movement of water in the system. Now we know that our P2 at our point 2, the pressure, is equivalent to the specific weight of water times the height of the water inside our container, which is approximately 20 centimeters. So this P2 value is equal to 9.8 times 10 to the 3rd newtons per meter cubed multiplied by the height of 0.2 meters. Now plugging and chugging into our equation, we're left with our P1 needed, which is 1 bar, over the specific weight of water, minus the height of the fluid in our container, which is water, and that gives us an elevation head of 10 meters required to have 1 bar of pressure inside our milliQ system. And currently, as you can see, we only have about 1 meter of elevation head right now, which is why the system is not working. So we will have to buy a pump to get the system to work. We can further explore the idea of the bulging sides of our container containing our fluid at our pressure point 2. That is due to the fluid force, resultant fluid forces acting on the sides of our container. Looking at this sheet and a diagram of the bin with our dimensions of 0.6 by 0.3 by a height of 0.2 meters, we can calculate the resultant fluid forces on the side of our container, the front of our container, and the bottom. The fluid force acting on the side of the container would be equal to 1/2 times the specific weight of the fluid, which is water, times the height of the water in the bin, times the area of the face, which gives us a fluid resultant force of 58.8 newtons. Similarly, we can look at the resultant fluid force on the front of the container, which is about the same, just multiplied by a different area dimension of 0.6 by 0.2. Resulting in a 117.6 Newton resultant force. And finally, the resultant fluid force on the bottom of our container would simply be equal to gamma times the height of the fluid times the area of the base of the container, which would be equal to a resultant fluid force of 352.8 newtons.